All right, only got one question this morning, and this was to go back over easy notation with alkenes. Now, when we talked about alkanes, no double bonds, we talked about using the CIP rules for establishing RS chirality. These exact same rules are used for establishing easy notation. Same thing. So barely you're going to see a lot of parallels from alkanes to up here with alkenes. So let's say we have some generic alkene. So we have A, B, D, and E. The reason we leave off C is carbon, so we don't want the confusion there. So there are different ways that we can orient things around this double bond. And the reason why we need to specify how things orient is that unlike an alkane where we can get rotational on carbon-carbon single bonds, these carbon-carbon double bonds don't rotate. So the easiest way to see this is if we work with cis strands. So when you did the rings for alkanes, you could do the cis strands if two groups were the same. If we have two hydrogens in two groups A and D, we would say that these are cis to each other. And if the hydrogens are on opposite sides, we could say this trans. And again, it doesn't matter. We just need two groups that are the same to use cis trans. But if they're not the same groups, we have to use EZ. And it's the same thing with alkenes that it was for cycloalkanes. We use the EZ when A, B, D, and E are all different groups. And we're going to base it off of atomic weight first. And if the atomic weight doesn't help us, we look at the branching. So your E here is Entgehen. And Z is Zusammen. And this is German for together. And this is German for opposite. So what we do is we use the CIP, the Konning-Ingold-Prelog rules, to determine out if we divide the bond in half, and we look at one. These would be Z notation. If D is lighter than E, so this is 2, this is 1, they're opposite, this is your Entgehen. So it's going to work just like it did for cycloalkanes. Now the EZ here is going to kind of show up like cis trans does. We don't like working with the EZ unless we can. We prefer the cis trans because that's a lot easier to work with. With cis trans, we're trying to see if A and E are the same group, this would be trans. If A and D were the same group, that would be cis. But in the event that we have 4 different groups bound to it, this is when we switch to the EZ. Now, the only way to really make this complicated, and I generally just don't do it because it's complicated for the sake of being complicated, is let's say it's an alkane, but we've got methyl, ethyl, propyl, and tert-butyl. For whatever reason, this is the alkane we're working with. For the EZ here, if you've just got nothing but alkanes, the one that branches first is the higher priority, the one that terminates first is lower priority. So since the methyl terminates before the propyl, or the ethyl, this is higher priority. Since this branches before this does, even though, let's see, 1, 2, 3, we can make this a butyl. This is 1, 2, 3, 4, this is 1, 2, 3, 4, they all weigh the same. Because this branches first, this will be top priority, this will be second priority, and since they're opposite, this will be E, whatever this complex is. But again, I think this is just kind of complicated for the sake of being complicated. The EZ, again, doesn't show up too terribly much, except when you get like really complicated molecules. For the most part, we're going to stick to the cis trans. So I'm not seeing anybody waiting. I've got the chat up if you've got questions, but if you've got questions, please feel free to post them. Otherwise, I'm just going to turn the camera off so I can get a little bit of work done. All right, so a question got asked about the IR and mass spec of alkenes. They're actually not that diagnostic. So typically when we look for the presence of alkenes, our protein NMR, our proton NMR, 1H NMR, and our carbon 13 NMR are going to be a lot more diagnostic. So the reason why I say they're not particularly useful, when we have an alkane versus an alkene, the alkane is 2 atomic mass units, AMU units, smaller than the parent alkane. So we have something like pentane versus any of the alkenes. So I put any of the alkenes here. The only thing that's going to change the mass spec is shifting things 2 units over for the parent ion mass. The problem here is that you're also going to shift all the other fragments. So you can't exactly like look at the different fragmentation patterns and say, oh, based on the fragmentation patterns, I can distinguish this alkene from this alkene, or this alkane from this alkene, simply because all the peaks are going to shift because this introduces new differences in terms of the stability of the molecule. So if we put a carbocation there, which is what we're going to do when we put a positive charge on it, the positive charge is actually stabilized by this alkene through resonance. So our mass spec is not very diagnostic at all. The IR, there are bending modes associated with your alkenes, but there's an issue with this. And so I don't have the tables in front of me right now, but there are numbers associated with it. What the tables don't really tell you is that these bending modes for the IR are actually very small. They're very faint. And so typically, especially if you have a large alkene, you're going to drown out the alkene peaks just due to the prevalence of the CH2, CH3, CH bending modes. So I would say neither the IR or the mass spec is particularly diagnostic. Now textbooks will say like, well, the IR does have this, the mass spec does have this. That's true, that's why the information is provided. But again, your NMR is going to provide a lot more information because by getting rid of these hydrogens, you're going to do by creating an alkene, you do 2 things. 1, you cut down on the number of hydrogens, which changes your multiplicity. And 2, they're actually de-shielded. And so these hydrogens that are inside alkenes, they actually connect to the double bonds. I'm updating some problems right now. It actually shifts at like 4 parts per million for the hydrogen. For the carbon 13, it shifts it down to 100 ppm. So your carbon 13, your 1HMR, this is really what you should be using to diagnose. But again, the IR and the mass spec are presented there because textbooks do like to say like, well, it does change the mass spec. That is true. It changes the stability of the ions formed. It does change the weight of the parent ion by 2 AMUs, which is really hard to see in a lot of these mass specs. And with the IR, yes, they do have bending modes, but these bending modes are not super pronounced and they're typically drowned out by all of the other alkane bending modes that are present. Wouldn't the peaks be less intense as well? Both in the IR and the IR, definitely. You kind of like especially if you have a single alkene. So let's say you have cyclohexene versus cyclohexane. You've only got 2 atoms really contributing to these bending modes now, but you've still got 4 here that are contributing to a CH2 bending mode. So just all things being equal, you expect this to be 4 times the intensity of this signal. And that's making a lot of big assumptions. If we actually know it's based off the bonds. So it's 1, 2. So you've got 6 bonds, only one of them is actually IR active towards alkenes. So you're not going to really see it, all things being equal. And even then, the alkene bending mode is not very strong. So they're not being equal. This rest of the signal is just going to drown it out. Yes, by IR is super great at diagnosing alcohols if you know that they're alcohols. So if you suspect that you have an alcohol in your mixture, that 3600 bending mode becomes really useful. Where you're going to see struggles with identifying alcohols is actually more of that proton carbon 13 NMR. You do get the singlet, but it's not a diagnostic singlet. Like you can have other reasons for having singlets in your molecule. So there's a little bit more ambiguity. But yes, you are right. With identifying alcohols, the IR is the diagnostic one. But we'll see when we start working on this unit, and particularly if you look at the synthesis problems in the packets, that's right, they're all carbon 13 and 1H NMR. Those are a lot better at diagnosing it. So typically when we're looking at the IR, what the IR really specializes in is non-carbon bending modes. So if you have OH groups, NH groups, SH groups, thiol groups, those are really easy to pick up in the IR. For mass spec, we're looking for massive shifts in atomic weight. You're going to accomplish this more with the halogen. So your alkyl halides are much easier to identify in the mass spec than they are in any of the other techniques. Yeah, so it's a matter of using the tools for the right purposes. If you're working with something that just has CHs in it, so in the case of alkenes and alkynes, this is where your 1H and carbon-13 NMR come in really handy because they can resolve those bonding environments and they can resolve what functional groups they're attached to. But carbon-13 NMR and 1H NMR, they don't probe oxygen. And so oxygen's going to show up more in the IR, and then halogens don't really show up in the IR. They are there in the 1H and carbon-13 NMR, but it's more of an impact on the shift. You have to know what this thing looked like in the NMR before you can figure out, and then let's see what it looks like afterwards in the NMR to figure out what happened. Your mass spec here is going to be more diagnostic. Naming alkenes. So yes, I've got the packets up. So we'll go through generically how you name an alkene, and then we can work a problem. So with alkenes, we're always going to have something out front to designate which way things are oriented around that double bond. The only exception here are terminal alkenes because there's nothing to orient. It's the end of the molecule. So the big shift between here and alkenes is that instead of having so let me start over. We're going to name it the same way when we start naming alkanes. So we want the longest chain here. So let's say I give you this molecule. 1, 2, 3, 4, 5, 6. So you've still got your hex prefix. And now we're going to add an E in E. And all this designates here is that we have a double bond. And so because the double bond is our only functional group, this is going to take priority over alcohol or alkyl halides and alkanes. It does not take priority over alcohols because alcohols are more reactive than alkenes. So next thing we need to do is name our branches. So we have 1, 2, 3, 4. Well, we got just the methyl. And the thing is that this alkene appear anywhere in here, so we're going to need a number in here to designate. Now, there's two ways to do this. We can put the number here, or we can put the number here. Generally, what you'll see, most people put the number out in front, just makes it flow a little bit easier. So we want to minimize the number for the ene. 1, 2, 3, 4, 5, 6. So this will be a 3-hexene. The reason why we don't have to designate it as 3, 4, it's implied that that 3 is the first carbon and the double bond. So whatever number you give, 1 plus that is where the double bond is. And now we've got our methyl group at 4. So the last thing we need to tack on, since this isn't a terminal alkene, is whether it's cis trans or EZ. Now in this case, I've got an ethyl group here and an ethyl group here. So I can easily just call this cis 4-methyl-3-hexene because the two ethyl groups are cis. But we can also do this by EZ. So like with cis trans, you could do EZ, but not the other way. If you had to do EZ, you couldn't do cis trans. We can also do cis trans EZ with these as well. The trouble with these is that cis and E and trans and S don't always, the cis trans EZ don't always match up. So they prioritize differently. Cis and trans prioritize the two groups that are the same. EZ prioritizes them by atomic weight. So to do the EZ, we're going to draw a line for the double bond. And we're going to look on the two halves. So on this side, we have a methyl group versus an ethyl. The group that terminates first is lower priority. So this is going to be number 2. And this is going to be number 1. Now hydrogen versus a carbon, pretty straightforward. So this is number 2, number 1. Since they are on the same side, they're zoosamin, they're going to be the Z 4-methyl-3-hexene. Now, the key only lists one or the other. I don't think I really went through and did the cis trans for all of them. If you see two groups that are the same, feel free to ask to see if they can be named cis trans. Again, just for the sake of writing the keys, there's usually only one answer provided. Now, if you have an alcohol group on here, alcohols take priority. So again, we're going to look at the we'll throw a halogen on here for good measure. So we've got 1, 2, 3, 4, 5, 6, 7. So this is a hep 10 all. So we had to put the E in there to designate that this is a double bonded molecule. Now, we're also going to put the all in here because it's an alcohol. One thing we are never going to have in this course is the alcohol adjacent to this double bond. If you go into 252, we'll talk about those are called enols, so they were a special class of alkene alcohols. But the first number here is going to designate the position of the alkene. This is going to designate the position of the alcohol because the alcohol takes priority in these reactions. We're going to name number closest to the alcohol. So this is a 3, 4. So 4 heptene 3 all. Again, the E here means you have a double bond. The 3 here, the OL here means you've got the alcohol. Now we just start numbering building our group. So we've got a chloro and a methyl. So we've got 4 methyl, 6 chloro. Last thing we have to throw on, and that's just what makes the names of these compounds super long and complicated, is the cis trans EZ. Now, we don't have 4 of the same groups here. We have a hydrogen, we have a chloroethyl, we have a methyl, and then we have this kind of alcohol propane group. So, what do? So, again, draw your line through the center. Hydrogen is definitely less than this chloro group, so this is going to be number 2. This is going to be number 1. On this side, we have a methyl group, CH3, and then we have a carbon bound to an oxygen. So, like you did for the CIP rules, we have a carbon with 3 hydrogens. Here we have a carbon with an oxygen, a carbon, and a hydrogen. So since this has got the alcohol bound to the carbon and this is just a methyl group, this takes higher priority. This is lower priority. Our 1s and 2s are opposite. They're entgane. So this ends up being E6 chloro, 4 methyl, 4 heptene, 3 all. So you make the decision between cis-trans means that if you look at the double bond, there are 2 things attached to that double bond that are the same. So 2 hydrogens, 2 methyls, 2 ethyls, something like that. If you don't see 2 groups that are the same, that's when you have to use the EZ. Now, the reason why we can't say that they're implying the same thing. So if I look at this complex, I can say that this is cis, and it's an ethylene, so it's 1, 2, 1 bromo, 1, 2, dichloro, ethylene. Now, this is cis because they're both on the same side, but if we look at priorities, on this side, this is the number 2, this is the number 1, and on this side, this is the number 1 because it weighs more, and this is the number 2. So in this case, these would be opposite sides, and so we would say that they are entgane. So the reason why that 90% of the time you are correct, they tend to get the same answers. So E and Z cis-trans tends to match up, but there are definitely cases, and they're not even too esoteric, where the EZ and the cis-trans give opposite answers, and it's just because of how they weigh priorities. Cis-trans just wants the 2 groups to be the same, and typically the 2 groups that are the same are the hydrogens when you look at most of the problems that people get presented with. Since hydrogen is always going to be the lowest priority, it always ends up being E to itself in the double bonds. But if you have a whole bunch of branches coming off of this alkane, this is where you start seeing the E and the Z start disagreeing with each other. Or if you have situations where you just have a whole bunch of heteroatoms, this is where they will start disagreeing with each other. Admittedly, these are kind of, I don't want to say esoteric, they're not that esoteric, but they're not common examples. Usually when we're talking about naming alkanes, we stick to very simple examples. Because of that, we always have hydrogens, and they make the EZ match up with the cis-trans. But again, you can easily come up with examples where this isn't true. So this was like, well, there are other examples. But the heteroatoms are where the EZ stop agreeing with the cis-trans. In this case, it's cis with regards to the chlorines, but by the priority rules, which is signed up by atomic weight, they're actually E, they're opposite. So they're trans in the EZ notation. Yeah, when I started tutoring organic chemistry about 3 years ago, just to kind of get back into organic, I had a student and I were sitting at the coffee shop in Mission Valley, and we were going through it, and we were like trying to figure out why EZ and cis trans aren't the same, because it looked like for most of the problems they were, but every now and then you come across a problem where they weren't. And that's where I finally sat down. I was like, oh, I get it now. It's when those hetero atoms start showing up. That's when it starts messing with you. Can we do another one of the alkane naming problems on the study packet? So yep, just let me know which, crap, I closed it. Just let me know which one you want to work on. Man, some of these have some long names. I'm assuming you're going through the packet to figure out which one you want me to do. I figured as much. I found 2 mistakes on these packets, which isn't bad for how many problems are on it, but I'm really annoyed that I found 2 mistakes on these packets. One of them was kind of a big mistake. Fifth problem on drawing alkenes, page 5. One, two, three, four. So I'm only seeing 3 problems. Maybe it's just the version of this one I have. So on the 5th page, the last one is a 3,1-methyl cyclohexene. That one I'm assuming you could do. So let's take a look at the E68 dimethyl 5-propyl dodeca 3-ene. So the dodec, I believe, is decane. Dodec is 12. So we're going to start by drawing out the 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the ene here is on the 3rd, so 1, 2, 3. Now, we've got the E, so let's see where everything else is first. So we got 1, 2, 3, 4, 5. So 5 here is the propyl. 2, 3, 6, 8 dimethyl, and we've got E meaning they're opposite. So we've got 2 hydrogens. We know these are lowest priority, they're opposite, so this would be the E form. Now, let's say we really hated ourselves, and first problem on page 5. Yeah, this is how you would do the E. The challenge with this one is you don't know a priori, which is E or Z, so you have to write the whole molecule out and then check your answer. So let's say this ended up being Z, and you drew this and you said, well, these are really E. In this case, easiest thing to do would be to take this double bond and just flip it. That's what I figured you meant, was the 5th problem in that set. The only difference here is that with the alkanes, you have the A at the end of the prefix. So instead, if you had 7, it was hept, plus the A made it hepta, heptanol, or hexanol, or things like that. You're going to replace that A with an E to designate that it's an alkene. And you're going to put a number now in front of the molecule to designate the position of the double bond. And you're going to have to do that notation where we put the number within the name to designate the position of the alcohol. But it very much follows from alcohol naming. You're just adding that extra little detail. I guess I can write it out. So if you had 3-hexanol, the A here meant an alkane. But now we can do, what we do now, if we want to convert it to an alkene, is we throw the number in there. So this becomes hex 3-ol. We add a number to designate the position of the alkene, and we switch this to an E to designate that it's an alkene. So that's how the switch goes. We have to put the number in there because it designates the position of the alcohol. The number out front here now refers to the double bond, and we switch the A to an E to designate the double bond. But yeah, if you think that this really follows from alcohols, it does. It 100% follows from the alcohol naming. And we'll start seeing this as we get further and further into more and more complicated functional groups. The highest priority group basically sets the naming scheme, and then everything else is just kind of tacked in there as details. Because the thought is that the highest priority group is the one that should be setting all the naming because it does all the reactions. You're welcome. You have a nice weekend too. Right, not seeing any concurrent viewers, so again, I'm just going to shut the camera off since I don't assume you don't want to listen to me type. All right, I'm not seeing any concurrent viewers in the last couple minutes here, so let's go ahead and sign off early. Again, if you have questions, please feel free to email them in advance, post them to the chat in advance. Go ahead and chat about them in the live stream. These are not lessons, these are not lectures, these are here for you as kind of office hours. So I will see you all Monday.